All right, so for the last talk of this academic year's eCHT research seminar, we have Cary Malkiewich, who will tell us about higher scissors congruence.
Thank you so much. Thanks for the invitation, and great to see you all virtually. As we're opening back up from the pandemic, I'm getting the chance to see more and more of you in person too, and that's been a real pleasure. All right, so this project is about higher scissors congruence, and a lot of this is joint work with Anna Marie Bowman, Tina Gerhardt, Mona Merling, and Ina Zakharevich. So the basic setup is let X be any standard geometry. So I'm thinking about Euclidean geometry, EN, or hyperbolic geometry, or spherical geometry. So any of these complete constant curvature geometries. This stuff can be done a lot more generally than this, but this is kind of enough generality for what I want to talk about today. So each of these geometries has an isometry group. That's usually a Lie group, but throughout this talk, I'm going to think of it as a discrete group. So this group has no topology on it. And I'm going to fix some subgroup G of that group. So again, this is going to be some discrete group G acting on X through isometries. So the basic setup is I want to consider polytopes in X, bounded non-convex polytopes. So to be more precise, the N simplex is the convex hull of N+1 points that are in general position. So not lying in some geometric subspace. And then a polytope is going to be any finite union of top dimensional simplices. Any finite union. So for instance, I could take this simplex, and then I could also take this one, and then I could take their union, and that's an example of a polytope. Of course, you could always subdivide it further so that it's a union where the interiors are disjoint. So if you like, you subdivide it further. Let's subdivide this one. Okay, and now all the interiors of your simplices are disjoint. Okay, so the problem that we want to ask about these, like the most basic problem about polytopes is, when are they isomorphic or when are they congruent? But here we want to talk about scissors congruence. In scissors congruence, basically, I want to allow myself to take my polytopes and cut them up with a pair of scissors and say, after cutting them up, can I make them congruent? So we say that P and Q are G scissors congruent if there exist almost disjoint covers. So I can take P and express it as a union of finitely many polytopes whose interiors are disjoint. Right, so think of this as here's P. I'm going to cut it up into finitely many pieces like that. That's an almost disjoint cover. And then similarly Q, I can cut that up into an almost disjoint cover. Maybe I should draw my example so that this works. Like so. And then there's scissors congruent if I can move every piece of P to a corresponding piece of Q and reform Q. And throughout that process, I'm only going to move by elements of G. So I'm going to apply these elements Gi that are in this fixed group G. So I drew an example up here. Here's another example. I can take a rectangle and I can cut it into two triangles like that. And then I can move one of the triangles over so that I end up with this parallelogram. So the rectangle and the parallelogram are scissors congruent, even though they're not actually congruent. Or I could take, for instance, a triangle, and I could cut it up like this, and then I could move these two pieces over. By the way, usually by default, G is the whole isometry group. So if I don't mention a G specifically, I actually mean for G to be all of the isometries of the geometry. So usually, G is equal to the whole isometry group.
So Cary, I was sort of thinking, just to have a non-trivial example of a G, that G could be like the translations.
That's a great example, actually. That will come up in the talk later in some of the computations. So I guess I should finish drawing out this example here. So I can take the triangle and rearrange it like this. So that triangle is scissors congruent to a rectangle. And more generally, in the plane, two polygons are scissors congruent. So if G is the whole isometry group here, P and Q are scissors congruent if and only if they have the same area. So basically, you do moves like this to rearrange them into rectangles. And you can show that any two polygons with the same area have to be scissors congruent. And that's an if and only if, right? Obviously, if they're scissors congruent, they have the same area. So to go for Dan's example, right, I could let G be the translation group on n-dimensional Euclidean space. So that's isomorphic to Rn. And then, so if I take a triangle and a rectangle with the same area, these are scissors congruent, but they are not T2 scissors congruent. It's impossible to cut up the triangle and using only translations, rearrange it to this rectangle. And the way you prove that is that you look in each direction. Like say I look at this direction and I take a sine sum of lengths of edges along that direction. This is called a Heidegger invariant. And then I show that that's invariant under translations. So in this triangle, I have a positive Heidegger invariant in this direction, but I don't in the rectangle. And so it's impossible to translate the triangle to get to the rectangle. That's a great example, Dan. Thank you. All right, so that's scissors congruence, right? You're looking at polytopes in one of these geometries, and you're saying, okay, up to this group G, can I cut one polytope into pieces and rearrange the pieces to make the other? There's kind of an obvious invariant here. They have to have the same volume, right? Because G is in the isometry group. So if they're scissors congruent, then they have the same volume. But the converse is not always true. Having the same volume is not always sufficient to argue that they're scissors congruent. So when people studied this, they found it very helpful. This was even before the homotopy theorists got involved. They found it very helpful to phrase this in the form of an abelian group. So this is the scissors congruence group. So here, X is my geometry, G is my subgroup of the isometry group. And I define this group P of XG by taking the free abelian group on all the polytopes. And then I mod out by two relations. So first, the class of P is the sum of the classes of PIs if the PIs form an almost disjoint cover of P. So in other words, if, I said this earlier, but I'll say it again, if P is the union of those PIs and the interiors of the PIs are disjoint. So intuitively, that corresponds to taking your polytope and allowing yourself to cut it up into pieces. So the class of the big polytope is the sum of the classes of those pieces in this group. And then secondly, the class of any polytope is equal to the class of G applied to that polytope for any G in my group big G. So altogether, these two relations impose the relation of scissors congruence. First, I can cut up a polytope into pieces. And then second, I can rearrange the pieces using elements of G. Of course, then using the first relation again, I can put the pieces back together. So if two polytopes are G scissors congruent, then that shows that they have to give the same class in this group. And the converse is also true, at least if G is big enough. So if it acts transitively on the geometry, passing to the abelian group doesn't lose any information. So we may as well phrase this in terms of an abelian group. As we know from forming, topological K-theory out of vector bundles, forming things into an abelian group is a very useful thing. It often makes things much more computable. Abelian groups are a lot easier to describe than sets, right? Okay, so let's do a couple of examples. So again, if G isn't mentioned, then it's just the full isometry group. So let's think about one-dimensional Euclidean geometry. It's just the line. A polytope is a line segment. And I'm considering these up to scissors congruence, so I can cut up the line segments and rearrange them. So clearly the length doesn't change when I do that. And if two segments or unions of segments have the same length, then I can relate them by scissors congruence. So as a result, this scissors congruence group is the reals corresponding to length. Of course, I have negative lengths here because in this group, I added formal inverses to all the polytopes. So I can have a formal inverse of a line segment, and that will have negative length. Similarly, as I mentioned before, so let's go to the two-dimensional Euclidean plane, two-dimensional geometry. Two polygons here are scissors congruent precisely if they have the same area. So as a result, this scissors congruence for the plane is also R, but it's a different R because now this R is counting the area of your polygons. Okay, so in 3 dimensions, it starts to get interesting. So I can take an R again, corresponding to the volume of my 3-dimensional polyhedra in 3-dimensional Euclidean space. And there's a homomorphism there because volume is a scissors congruence invariant. But that's not the whole group. So there's a second invariant taking values in R tensor R mod Z, or if you prefer R mod pi Z. This tensor product is over Z. And this is called the Dane invariant. So the Dane invariant is basically taking a sum over all the edges. So over all the edges of the length of that edge, that's an element of R, and I tensor with the angle formed between the two faces that are incident at that edge. So this is an edge of the polytope. And here are the two faces that are meeting at that edge. I'm going to take the angle formed between those two faces. So that turns out to also be an invariant. And if you put them all together, then this map becomes injective. So the injectivity of this is called the Dane-Seidler theorem. And it was proven by Seidler in 1965. And was formulated this way by Jessen in 1968. This Dane invariant was defined in 1901. So in 1900, Hilbert, in his famous list of problems, the third problem in that list, Hilbert's third problem said, basically, is the polytope group R? In other words, is volume a complete scissors congruence invariant? So Hilbert's third said, is this polytope group? I mean, he didn't phrase it in these terms, obviously, but this is the content of his problem, right? Is that third polytope group R? Is the volume the complete invariant for scissors congruence? And Dane showed the answer was no, because he used the Dane invariant to give examples of polyhedra that have the same volume but different, are not scissors congruent. And then Seidler showed that this is injective. In fact, this is part of there's a 4-term exact sequence you can write down. So in a sense, you can completely compute what this group is. And then later, so this was work of Jessen. So there's a similar result for 4-dimensional geometry. There's a co-dimension 2 Dane invariant here that sums over the faces now. And we again get an injective map. So this is Jessen, 1968. And then for 5-dimensional geometry, it's just open. We don't know what this group is. There is a map to volume plus a Dane invariant plus another Dane invariant, but we don't know if that map is injective. And furthermore, even describing the group that the second Dane invariant lives in is kind of messy. So this quickly becomes a very difficult problem. I won't say that much about spherical and hyperbolic geometry, but it's a similar story in those. We basically know what the answer is up through dimension 3, maybe in dimension 4, but once we get to dimension 5, we don't know. And to come back to the example that Dan suggested, we do the translation group. So if we go back to 2 dimensions and consider polygons, but only up to translation, we now get the area again. But now we get a bigger invariant. So we get a sum of copies of R, 1 copy for every point in RP1. So like for every line through the origin, we do a signed sum of lengths for edges that point in that direction. And that turns out to be injective. And the co-kernel of that is a single copy of R. basically you take all these R's and you add them together to make one R. Because if you take the sine sum of the edge lengths, when you go around the polygon, their sum has to be 0. Because if you add these vectors together and it closes up to form a polygon, then the sum of the vectors is 0. Okay, so we also know what these groups look like for some other subgroups of the isometry group as well. Okay, so that's classical scissors congruence. Classical scissors congruence is polytopes up to scissors congruence. We can form an abelian group out of it. We can compute that group for a while, and then it's hard once we get to dimension 5. Well, this talk today is about higher scissors congruence, right? I want to suggest that these, I guess I should scroll back up here. I want to suggest that these groups are the lower homotopy groups of some interesting space or spectrum, and that the higher homotopy groups of that spectrum are interesting as well. And you can kind of guess what the spectrum might be, because if you stare at relations like this, maybe this is screaming K-theory at you, right? Doesn't this look like a form of K-theory? I'm taking some free abelian group. That's like taking the free abelian group on modules and then saying, oh, the class of P direct sum Q is the class of P plus the class of Q. So Ina took this idea and ran with it. So the way you set it up is we form a category, PXG, of polytopes. So the objects are just going to be polytopes, P, inside our geometry X. So the morphisms from P to Q are going to be given by an element G in G, such that when I apply G to P, it lands inside Q. So here's P. I'm going to act by an element G to get GP, and then I'm going to ask that that lies inside Q. That's my category. Pretty simple. So inside that category, I can now take tuples of morphisms, and I can say that they form a cover if Q is the disjoint union, Q is the union of all the images of these polytopes, and the interiors are disjoint. So if I have my polytope Q here, and if I map into it from 3 different polytopes, and that one, and that one, right? That's an example of a cover. P1, P2, P3. Seems pretty related to scissors congruence, right? Okay, so now I'm going to form a category out of these covers. So I'm going to form a larger category. Now I'm going to start taking formal disjoint unions of the polytopes. So in this category W of P of XG, the objects are now finite disjoint unions. Well, actually, I should say finite formal disjoint unions. I'm allowed to take the same polytope and repeat it n times if I want. That's fine. But I consider that as a collection of things that are formally disjoint from each other. And then if I want to map from one finite collection of polytopes to another finite collection of polytopes, what are the morphisms? Well, I have to pick a map of sets from I to j. And then I have to pick a map from each pi to q of f of I. So this map is going to be by an element gi. I apply some group element. Basically, I'm applying a group element to put pi into one of the qj. And I want this to be arranged so that if I take one qj and I take all the pi that hit it, so I take I in f inverse of j, I want this to be a cover. So in this category, my objects are finite lists of polytopes, and my morphisms basically allow me to glue the polytopes together without substantial overlap. The interiors always have to be disjoint. And when I glue them also, I can only move them by elements of G. Again, so if I'm in the translational case, I'm only allowed to translate the polytope. Okay, so it's kind of an observation that in this category, P and Q are G scissors congruent precisely if they're in the same component, right? If I can cut P up into pieces, well, that's a cover. And then when I rearrange the pieces by elements of G, that's an allowable morphism. Right? I could take F to be the identity map, just apply a group element G to each one. And then I assemble the results back together into Q, that's also a cover. So this categorifies the relation of scissors congruence. But of course, this is a category. So I can take its classifying space, and then I can take the group completion of that classifying space. So this is Ina Zacharevich's definition of scissors congruence K-theory. We take the classifying space of this category. This forms a monoid, or a Siegel space or an E-infinity space using disjoint union of the collections. And then I can group complete that to get a spectrum. And that's scissors congruence K-theory. So you think of this as like, I took some moduli space of polytopes and maps between them that cut the polytopes up and rearranged by elements of G. Scissors congruence K-theory is the group completion of that moduli space. Okay, so when you work this out, the lowest K group, in other words, pi naught of the space after group completing, is exactly the classical scissors congruence group. Classical scissors congruence group, PXG. Right, so again, this was the free abelian group on the polytopes, modulo those two relations. If I have cut one up into pieces, the class is the sum of those classes. And if I apply a group element, I get the same class. On the other hand, now that this is a space, it has higher homotopy groups, right? So we get a natural notion of what are the higher scissors congruence groups. So for instance, what's K1? So Ina computed that K1, so here this is one-dimensional Euclidean geometry, and I'm taking the translation group. She computed that it was the exterior product of two copies of the reals over the integers. So to be a little bit more concrete about what this is, so if I have, now let me write down here, right? So say I have a polytope and I have what you might call a scissors automorphism. So in other words, I take the polytope, I cut it up into pieces, and then I rearrange the pieces to make the same polytope again. All right, so P, and then I have some cover by a bunch of PIs, and then I have another cover. So by going around that circle, I've cut it up and rearranged them in a non-trivial way. That scissors automorphism is always going to define a class in K1. So in this group, if I take X wedge Y, this corresponds to the scissors automorphism of an interval. I assume the interval has length X plus Y, and it's the automorphism that cuts into two pieces and then rearranges the two pieces. So that's what the generators of this group correspond to. If I take all isometries, it turns out the group is 0. So it's also generated by these swap maps. And then using the fact that you can reflect orientation, you can show that these elements cancel out and I get 0. So this is a little taste of these higher scissors congruence groups. We could keep going and say, what's K2? But like the method that you use for K1 doesn't obviously generalize. You can start to produce some classes in K2 by giving pairs of commuting automorphisms, but it becomes a lot harder to tease out like what is the group actually. And this is the computational homotopy theory seminar, right? So the goal here is compute. Right, what is this group? So let's state this as the higher form of Hilbert's third problem, right? Hilbert's third problem was about computing K0 of the spectrum. So the natural higher form is to compute the scissors congruence groups.
Can you explain your picture once more time for the K1?
Oh yeah, absolutely. So this picture here?
Yes, please.
Okay, so, right. So I'm gonna map this interval back to the interval. Let me do it this way. I'm gonna send the X here. And I'm gonna send the Y here. So this is a scissors automorphism from the interval of length X plus Y to itself. Does that make sense?
Yeah.
Okay, great. So the idea is this is giving you, like intuitively, this is giving you a loop in the classifying space of this category, because I'm going from an interval of length x plus y, and then moving through the category, I'm cutting it up, and then I'm putting them back together in a different way. So that's giving me a class in pi1. And Ina proved that all the classes in K1 arise this way. Kind of like for how K1 of a ring, or I guess K1 of a field. In K1 of a ring, everything is represented by a single invertible matrix. And in K1 of a field, it's always represented by a unit. Okay, so that's the setup. So we want to try to understand something about these higher groups, right? What can we possibly understand about them? So the first theorem I want to present, so this is joint with Bowman, Gerhardt, Merling, and Zakharevich, is that the spectrum is actually a homotopy orbit spectrum. So it's constructed as K-theory, it's constructed as a group completion, but it turns out to be K-theory of some very special kind of object that allows you to pull homotopy orbits out. So this K-theory spectrum, K of P of xg, is K of P of x1, homotopy G orbits. In other words, if I never have G act on the polytopes, this is like a standard thing in equivariant homotopy theory, right? If you build an object in which, nothing is equivariant, then G acts on the result. So here, if my maps between polytopes never move at all, I'm just subdividing them and that's it, then there's a residual G action on the whole space. And so we proved that the homotopy orbit spectrum of that is Scissors Congruence K-theory. So you can think of this as like a Farrell-Jones isomorphism, right? This is a setting where you have some natural assembly map from homotopy orbits into an equivariant K-theory. And in this special case, this assembly map is guaranteed to be an equivalence of spectra. Right? In other settings where you have assembly maps, you can formulate something similar to this, but they're not always equivalences. So one thing that's really cool about this is that this allows you to define a trace map out of Scissors Congruence K-theory that lets you pick off some of the higher classes. So the way this works is...
Sorry, can you repeat what G and 1 are here?
Yes, so G is a subgroup of the isometry group. And so 1, I'm going to take to be the trivial group.
Great.
Yep, so this is like Scissors Congruence, but I never allow myself to move anything. So everything is just staying in place. Ina likes to call this no moving. Scissors Congruence. So if you take no moving Scissors Congruence and then take its homotopy orbit spectrum, you get Scissors Congruence. You get G Scissors Congruence. Okay. So what is no moving Scissors Congruence? So, on pi naught of this thing, so, pi naught, let me put it up here. Pi naught of, or let me call it K naught, of P of x1. So that's free abelian group on the polytopes. And then I'm only modding out by this relation that if there's an almost disjoint cover, the class of P is the sum of the classes of the PIs. So I can take the volume of those polytopes and map this group to the reals. If I do that, that's a map from pi naught of this spectrum to the reals. So it gives a map from this spectrum to the Eilenberg-MacLane spectrum of the reals. And now taking homotopy orbits, this becomes Scissors Congruence K-theory. This becomes a spectrum where at each level, it's just the group homology of the group G with coefficients in the reals. So I want to emphasize again here that G is considered as a discrete group. Right? Oftentimes it's a Lie group, but in this setting, we're forgetting its topology. We're thinking of it as just a discrete group. Okay, so at level 0, this is mapping us from the classical Scissors Congruence group to R. But that's pretty boring, right? That's just going to take every polytope to, where'd my pen go? That's just going to take every polytope to its volume. Right? We kind of already knew that that was a homomorphism out of the scissors congruence group. However, if we go up to K1, this gives us a really interesting new invariant. So the first group homology is the abelianization of G, and then, you know, universal coefficient theorem, I extend scalars to R. And so if I have a scissors automorphism, it's going to get sent here to the sum over all the pieces of the element of G that I applied to each piece, tensored with the volume of that piece. And if you similarly have a class in higher K groups that's described concretely, like actually writing out the class in the moduli space, you get a similarly explicit description of this trace. So this trace is a pretty explicit computable thing. For instance, there is this group I mentioned earlier. So if I do K1 of polytopes in the line with translations, so that's R wedge R. This trace gives me a map to R tensor R. And the map sends X wedge Y to X tensor Y minus Y tensor X. So in that setting, this trace map is injective, seeing everything. So we kind of gave a larger example. So this is in two-dimensional space. So here is a polygon. Okay, so this whole thing is supposed to be describing a class in K1 of polytopes in the plane, where I'm going to use oriented. I'm going to take the subgroup of oriented isometries. So what I do is I take my big square, I cut out a square inside whose area is equal to X, and say it makes an angle of theta. I rotate that square so that it becomes perpendicular to the sides of the original square. And then for all of these other pieces, I cut them up and move them over, but I only use translations. So in other words, the square is the only piece of this that's rotated. The rest of the pieces are done by translations. So if you believe you can do this, and look in our paper, there's a really nice illustration that actually shows you how it's cut up into pieces and rearranged. This is going to define a class in the abelianization of SE2 tensor R. So what is this going to be? When you abelianize the isometries, every translation is a commutator in terms of rotations. So all the translations go away, and you end up getting just R mod 2 pi z. So you just get the rotations, SO2. And so as a result, only this piece is going to contribute to the trace. So I end up getting theta tensored with this area X inside this group. But in particular, right, this is usually not zero. And so this constructs a new family of non-zero classes in this K1 group. All right. So this trace map on the higher K groups it's actually non-trivial, right? It's computable, it's non-trivial, it's everything that we love about an invariant. Awesome. All right.
You get a new proof of the Pythagorean theorem out of knowing. It's mostly a joke, but
Jack Morava asked us that question this weekend when we were talking about this
All right.
over the Mid-Atlantic topology seminar.
darned it. Okay.
Yeah, we were thinking of saying something like, oh, we're giving a parametrized family of proofs of the Pythagorean theorem that are all classes in K1 here. Yeah, I mean, this basically is one of the classical proofs, right, of the Pythagorean theorem. Awesome. Okay, so that's fun, but so this result, I guess I should scroll up to the earlier result. Right, so we proved that the scissors congruence K-theory spectrum is a homotopy orbit spectrum, but that just kind of raises a really obvious question of okay, great, what is it homotopy orbits of, right? What is the homotopy type of this thing? Because if you understand that, then you've basically solved the problem, right? You understand what is it homotopy orbits of, take the homotopy orbits, and boom, we know what scissors congruence K-theory is. All right, so that's kind of the big overarching goal here. Okay, so what about this? What if I take no moving and I build the spectrum, what do I get? Well, I should mention, first of all, I guess I mentioned this already, at the level of pi naught, we get something that we already knew. So we get the scissors congruence group with no isometries. And this is sometimes called PTX, the polytope group. So this is the free abelian group on polytopes, but modulo, I can cut a polytope up into pieces, and then P is equal to the sum of those pieces. So you can describe this as like, this is measures on the geometry that are generated by indicator functions for polytopes. Right, because if I cut this one up into pieces, then as a measure, these are still describing the same measure. So classically, the way that you would actually do this computation is you would cut it up into two pieces. This kind of echoes the theorem that we proved. You would first try to understand this polytope group, and then you would take the covariance or zeroth group homology. In other words, you'd mod out by the G action, and that would give you your scissors congruence. So what do we know classically about this? This is actually a free abelian group. It's not obvious from the definition, but if you take this free abelian group and you mod out by these relations, you actually get a free abelian group again. Not in any canonical way. There's no canonical choice of basis, but it is isomorphic to a free abelian group. Okay, so that's a good start. So we're trying to get the homotopy type of the spectrum. We know at pi naught it's a free abelian group. That's a good start. So what are the higher homotopy groups? Okay. Well, what Ian and I proved is that this spectrum is a wedge of sphere spectrum. It's a wedge of S zeros. So in particular, at pi 0, I have one sphere for every one of these Z's. So you can think of it as a wedge indexed by some basis for this polytope group of copies of the sphere. And that implies that the higher homotopy groups are going to be the same polytope group tensored with the higher homotopy groups of spheres. Or at the level of the spectrum, this is some wedge of spheres, and then I'm taking the homotopy orbits of that. Wow, awesome. Right, great. This is getting way simpler than we expected, right? This algebraic K-theory is kind of breaking apart, but not so fast. So I mentioned, right, there's no canonical choice of basis here. And so that means that there isn't, we're not just having a G action on this set and then quotienting out by the G action, right? If we did, then we would be getting some wedge of classifying spaces, and that would be a little bit too simple. That would mean that pi naught is free abelian, and we already know that pi naught is not free abelian. In the examples I showed you, it was R, or it was something bigger than that. Okay, so in particular, we get a spectral sequence. So, the homotopy orbit spectral sequence, or a Tia-Herzebruch spectral sequence. So homology of G with coefficients in polytope group tensored with stable homotopy of spheres goes to scissors congruence. Kp plus Q of polytopes in X up to the group G. Okay, yeah, cool. Spectral sequence, getting closer. In particular, and stable homotopy of spheres is hard, but rationally it's not hard, right? If I rationalize the rational scissors congruence groups, rational scissors congruence is isomorphic to group homology. It's homology of the group G, but with coefficients in this polytope group. It's group homology. Huzzah. So in particular for dimension 1, you can just calculate what this group homology is. You can do a little bit of homological algebra, and you can see that the higher K groups, so if I'm in the line and I take translations, are going to be exterior powers over the integers of copies of R. So this generalizes Zacharevich's computation of K1 as R wedge R. If I take all isometries, I'm going to get the same answer. Why do I want to make that an A? That's a lambda. Lambda m plus 1 z of r. If m is even, and I'll get 0 if m is odd. All right, rationally, there's no torsion. And so when you're modding out by an extra z mod 2 here, you just have to cancel out some -1 eigenspaces. And so you keep the +1 eigenspaces. Yeah, all right. So this gives us the rational higher homotopy groups. And you can, maybe I should scroll past this. You can go even further. You can give all of the rational higher homotopy groups for the two-dimensional geometries as well. You can phrase them all. So for Euclidean geometry, you can phrase it all in terms of the homology of the group of Euclidean isometries. For hyperbolic geometry, it's phrased in terms of hyperbolic isometries. And for spherical geometry, it's in terms of the orthogonal group. So in a sense, this problem, it's reduced to a computation of group homology. Of course, that computation is very hard because, this is a Lie group that I made discrete. So I mean, who on earth even knows what this homology group is? All right, so out of this, is K1 0? I don't know. Out of this one, we can say that K1 is rationally 0. Okay, so scrolling back up to this. So we can rationally compute these higher scissors congruence groups. Now, we want to go a little bit farther. It would be nice to say something about the torsion. But to do this, we have to kind of unpack a little bit what's going on in that spectral sequence. And so we have to understand these homotopy orbits a little better. In particular, we have to give an equivariant description. The description that we gave as a wedge of spheres was a non-equivariant one. And so we don't really get any information about, to plug into the homotopy orbit spectral sequence, other than the G action on homotopy groups. Okay, so to do this, we have to take that free abelian group I mentioned earlier and build a topological version of it. So the way you do this is as follows. So here X is a geometry. I'm going to look at all of the subspaces that are geometric subspaces. So if you like, they're complete geodesic subspaces. So in Euclidean geometry, this would be all the points, all of the lines, all of the planes, etc. Not necessarily through the origin. Okay, so I have a diagram where I go over all the subspaces of the geometry, where I just take the subspace itself. I can take the homotopy colimit of that. Of course, that's just isomorphic to X. That's equivalent to X, because X has a terminal object. And then I can mod out by the homotopy colimit where I take all of the proper subspaces. This is kind of hard to see, but it's important. Right, I take everything other than X, and then I quotient that out. So it's a little bit like taking a total homotopy cofiber, right? A big homotopy colimit modulo a smaller one. You can show, this is a version of the Solomon-Tietz theorem, you can show that this space is equivalent to a wedge of n spheres, where n is the dimension of the geometry. And that lone homology group you get is exactly this polytope group. Well, what's better is that this space kind of has an obvious action of the isometry group, because I built it out of subspaces of the geometry. Okay, so now how do I get down to 0 spheres? Well, I have to desuspend, right? But remember, I want this description to be equivariant, so I have to desuspend by the correct thing. The correct thing turns out to be the tangent bundle. So you take the tangent bundle of the geometry, that pulls back to the space, away from the base point. And therefore, I can take a reduced suspension of this space by the negative of the tangent bundle. And so the answer turns out to be, that is the correct equivariant description. So if I take those n spheres and desuspend them by the tangent bundle, that's a wedge of 0 spheres, and that is equivariantly the correct spectrum. So taking homotopy orbits, we've now described scissors congruence K-theory as homotopy orbits of a Thom spectrum. That is again a Thom spectrum. So scissors congruence K-theory is the Thom spectrum. Did I write that below? Yeah, okay. No, I did not. Scissors congruence K-theory, surprise, surprise, is a Thom spectrum. It's kind of a better description than we, possibly could have hoped for. So once you have this description, you can now actually go on and prove in the Euclidean case, the spectrum is actually rational. Like all the torsion cancels out. And so as a result, this computation that we did rationally is actually the integral computation as well. And so this gives us the first case above K1 of a computation of the higher scissors congruence groups. Of course, this is for one-dimensional geometry. We know that for five-dimensional geometries, already at K0, it's an open problem. So it becomes kind of an interesting question of, from here, how much farther can we push it? Okay, that's all I'd like to say. Thank you so much.
Right, let's thank Cary.